And there will be question and answer sessions between the presentations. Then over to you, Dr. Gous.
Thank you. Thank you so much. All right. So welcome. This is now the third session of M2 indeed. And so we are now going to kind of move on towards better structures on your robot. So whereas when we started in M1, we just built a basic chassis, and then we did some basic navigation, straightforward navigation. In M2, we kind of upped the programming. So we introduced for loops, and we introduced decisions, switches. And so we played around with that. And then to make that more effective, we then also use input data so that you are using sensor data so your robot actually knows what's going on in the environment. Okay, so for today, we're going to now upgrade the structure of the robots. And so up until now, you've just seen this basic Riley rover with a passive attachment on it. So now what we're going to do is we're going to add powered attachments onto it. And so I just want to kind of show you some examples of a powered attachment. So the powered attachment is any attachment that, number one, is attached to a motor. So there's movement in it, so you can program it. So here's a robot Mozart, and it's got in here, it's got an arm. I don't know, you can see the motor there, the motor and the arm, and this controls this arm. So there's your arm going up and down. So that you can actually program. You connect this motor to port A or any port, and then you get motion. But this is one level of it. So what happens is that and if you look at the Riley rover, I'm going to show you some examples now. You have the basic motion to close the arm, open the arm, lift the thing, close it. So those are your powered attachments that you can program then to move. And can I ask that you please always program powered attachments on time? Often the learners don't put the starting positions accurately, and then the robot cannot complete the rotations required of an attachment, and so then the robot just stands. All right. I just want to show you something else. So one of the things with attachments is that it needs to be really clicked on and clicked off. And to that end, there's a really nice example of dog gears, and I'll give you an example of that. But what we have here, I have a little spiky that was built. You can see inside here, there's really good gearing over here. So this is a bevel gear, and that lifts that arm up and down, which is then linked. So the cool thing about this is that this attachment actually, now I want to show you how I'm doing it. Now, hang on a minute. Can you see here? So it actually lifts off. So there you've got the pins at the bottom, there underneath, you've got the pins, and it actually pins onto it. So you'll say now, okay, so what is it pinning onto? It's pinning onto the motors here. All right, so there are the motors, and it turns, and then the attachment is then pinned onto it, pinned on and pinned off. And if you have a dog gear, you can take it off and put another attachment on. So what we're aiming for as we advance with our learners with their problem solving is for them to come up with these structures. So that said, I have a collection of amazing structures which my teams have over the years used, and yes, they've used them, and so they're attached to various robots. This one attaches to the Mario, and so this, with this gearing over here, this arm goes down and had to do something, and I'm kind of thinking it was hydrodynamics with it to flush the toilet or something. But so very specific. But so what we're departing from now is having very specific building instructions, and you want your learners to start designing their own attachments. And in that lies the investment of time. Okay, it doesn't come naturally. All right, and we need to. I'll show you where to start. And then what you want is learners to start developing like attachments for their robot, and so the robots can attach at all things. So if I just want to show you here, sorry, I just want to just detach this thing here. All right, so if you look over here on this robot, you can see under, this is the Mario robot, but you can see in front of it, it's got these two knob gears. Okay, and the cool thing about these knob gears is that inside of this chassis are 2 medium motors. So what the team has are a collection of attachments that click onto the front of the robot, and then use these, because you see the motors inside here. All right. So it's not one attachment on a motor, it's motors, and then you attach the power attachments to that. But there obviously has to be some other linking mechanism, a gearing mechanism. So you have to use gears. Okay, so that's where we are. That's what we're going to do today. And let me share my screen, and then we have this whole conversation of whether you can see my screen and with whatever. All right. Am I sharing my screen? Not yet.
It's not going through on my side.
There we go.
Yes, I can see.
Okay, and I'm going to, there we go. All right, here we go. Okay. All good?
Yes, all good.
Okay, all right, awesome. So really you're on M2 already, and we're on the second half of M2. So you really are, just keep going. Now you need to keep going. So now what we're doing is gearing and power attachments. So, and this will really concentrate on the engineering part of it. It's a huge field. This whole thing of power attachments is huge. But again, we need to create a frame of reference. Okay, so there's our navigation issue information. Tumelo and Anzani are on the emails. Please shout if you need any help. And the content is on M2. All right. We really need competent and confident coaches to ensure that we have competent and confident teams. All right. So it's the next step. We've done the Riley Rover. Riley Rover's done and dusted. We now need to take our learners to a next level, and that includes upping the programming with sensory data or sensor data, using different programming structures, but also to up the structure of it. And so we need to have gears, we need to have power attachments, and there's a plethora of examples that we can use. Okay. Oh, well, so if you're in the amazing race, you're on the downward hill already, so you're nearly home. And but really, we really appreciate questions, whether you can ask the questions now or later or in the QA. It's all good. Just ask the questions. All right. So now we're on to the power attachments. We're building it, but for better and more effective and more efficient, more reliable power attachments, we have to address the topic of gearing. Okay. And there's building and there's programming of that. All right. So you'll see in the overview document on M2, there are a number of objectives. You do need to actually build the gear models, and I would really encourage you to build a couple of the gear models, and then to actually write some programs to see how to control, because the programming must be modified if you're going to use gears. Okay. So there's kind of two parts. First, we do the gearing, and then we're going to do the power attachments. All right. So there's two parts to this session. And once we've built the model, you need to actually write the code. So, and test each combination. Really important, because otherwise you're not, the gears are just going to be nice pieces in your robotics kit. And that's not what we want. We want more effective, more efficient robots. Okay. So if a gear is a machine that rotates, and this whole thing of the teeth meshing, you must ensure that it actually meshes, because if it slips, then you're lost. Then it's just a total mess up. But you need to be able to mesh so that you can transmit the power, all right? And so there's various ways of actually doing of the meshing, because remember, sometimes we go at 90 degrees, and so then there's direction. Sometimes we go from rotational to linear movement, and so all that needs to be more explicit. I think when you start with your learners, and you're going to have to repeat this several times, they've probably heard of these things, but we're now on to practice. We need to be able to implement it. Okay, so just in case you haven't found the gears in your box yet, your gears look a lot like this. A lot of teeth that you put together, and so there where it joins together, that's the meshing. And if you put a whole lot of gears in a row, that's the gear train. Obviously, if you turn this one, this little one's going to turn 6 times before this big one's going to turn about, I don't know, once. And that it depends which is your drive. If that's your driver gear, then that so that one drives this one in the opposite direction, then drives the other one. You're going to have to rotate 8 times to get that one to rotate. However, if you make the bigger one the driver gear, one rotation of this is going to cause like 8 rotations of that. Okay, so you can see, gearing up and gearing down that you can get. Okay. And then if you go linear to so if you're going to turn the pinion, then the rack is going to go left and right. All right. That's also an option. And then the 90 degrees is with the bevel, where you make bevel. I showed you one example as well, where you have 2 angles, 2 gears at a 90-degree angle. Okay, so the most important ones that we do use are just the spur gear, the crown gear, not that much. But the bevel gears. So spur gears and bevel gears a lot. Double bevel gears, not that much. But the worm gear is a good one. And the worm gear is on one of the powered attachments that I'm going to show you. It's really good to make a start. Okay, and so the learners must understand what you're turning and what you're not turning. Okay, so you turn the worm gear to make the spur gear turn. Okay. The clutch, I have not ever used that in a robot yet, but the knob gear a lot. The knob gear is one of those good starter gears because the learners can engage with it. It meshes well if it's in a good structure. It doesn't slip as much as this, like the spur gear is meshing. So a knob gear is really good. Of course, it looks like the top of a tap, but yeah, but it's not. Okay, a lot of good resources for gears, but gears are also in the technology curriculum, so there is quite a bit of information about gearing. All right. Okay, so when you do a spur gear train, the driver gear is the one that's attached to the power, and the other one is the opposite direction. And so that was one of the first encounters that I did of robotics, with my daughter coming home and telling me there's little arrows here. So the one goes this way, and then the other one goes that way, and then the other. Well, you know what? As long as the children can explain it, I'm happy. But the adjacent gear always moves in the opposite direction. Okay, and you'll be able to demonstrate that as well. Again, with the rack and pinion. So if you're going to turn, then the rack will move up and down, and the pinion will rotate, because there's the axle. There's the axle that's attached to the motor, and then the rack will move up and down. Okay, so the axle is attached to a large motor. Attach it, you see, and then test it. So if you attach the gear to the axle, and then you let this run to see the effect. Okay, and then but test it well, so you can maybe test the power settings and see how it goes. And for everything that you do, you must be able to kind of explain why it's working and why it's not working, because sometimes it's a bit fast. Okay, right. You've got to be able, learners need to be able to describe impact. Okay, so when you have bevel gears, you usually have them at 90 degrees, something like that. There is also, I'll show you an example now. But it must be well meshed, otherwise the thing is going to slip, and there's nothing more. If you hear gears that are slipping. All right, again, 50% or 100% of power, and then the learner must be able to describe the impact of the different power settings. All right, so we've got all these gearing options, and the question is, okay, so how do we use this then in the powered attachments? So that first and foremost, the most important thing of a powered attachment is that it has a motor attached to it. So if it has a motor attached to it with a wire, then you are able to program it. Okay, so the powered attachments are always attachments on a robot, and they're usually attached to a motor, and you can use gears, which I would suggest, and then it might require some programming. But there are, so the question is, where do you put a power attachment? Well, it actually depends where you need it. So do you need it at the front, the back, the center, wherever you need the robot, and it's usually an arm it's usually an arm that we attach as a powered attachment, or you've got a grabber, or you've got the cargo loader. So then it depends where you need it. Okay, But a power attachment must be connected as a structure. So as a structure, you need to have the wiring, the beams. Well, you need to have the, first of all, the structure is the connectors, and then you need to have it wired for the actual function of the thing. Otherwise, you're not going to, nothing's going to happen. And I can put my money on a block. Somebody somewhere along the line, one of your learners is going to come to you and say, man, the power attachment doesn't want to work. And then it's because the wire hasn't been connected. I bet you. All right. So these are examples of attachments in the Riley rover. And as I said, the Riley rover kind of makes a good start. Okay. And whenever you have powered attachments, there's always a, what is the verb? What do you really want to do? Do you want to grab it? Do you want to lift it? Do you want to push it? Do you want to drop it? Do you want to pull it? Okay. So that all determines what attachment you are actually going to use. All right. So over here, this is the cargo loader, and this, you can see the knob gears that goes up and down. And this one is then a worm gear here in the middle with spur gears. And so that is grabbing. But not all grabbing is the same. So these two little arms that grab might be fun if you're going to grab something light and something like a ball of wool. It's not cool to use that grabber to grab a full bottle of water. Okay, so that's where your innovation, your team's innovation and design comes in, is where they take a structure which you've taught them as a like a frame of reference, and then what you need to do is then you need to say, okay, so how are we going to then modify it? All right. And yeah, so also here you can modify. This one lifts up, all right, so it'll carry something, but you could also just turn it around and then it'll be something that goes down and pulls, so you can gather something. All right. So I've got closer pictures. So they're connected. I don't, you can see that so clearly. But basically, the motor is underneath the robot, and then that wire is connected to port A. For cargo connector, again, the medium motor is underneath, and the wire then is connected to port A. Okay, so if the gripper arms are modified, you can do a lot of things, additional functions. All right, so again, there's Dr. Hino has got some really cool ways of demonstrating this. He kind of uses the Riley rover attachments to really demonstrate that you could not necessarily most effectively and efficiently, but you can use these just to do most of the robot missions on any first Lego League mission. Okay, here's a close-up of the arm that goes up and down. So it's going to go up and down, but you see there are the gear, the knob gears, so they're meshing. And then the arm goes up and down, so you can lift it up, lift it down. So one of the modifications as well is to say, well, if you put something on, it's going to fall through. Well, then maybe you need to modify it. Okay, maybe you need to make it smaller, then you make it small. If you need to make it larger, then you make it larger. Whatever you're doing, you at least have the mechanism sorted. Okay. It's exactly this with the spur gear and the worm gears. So in there is the worm gear. And I will tell you now an error that most learners make, that there where the axle is, your axle must be able to turn there. And if it's not a, there must be no holding that one there. If your motor doesn't turn, then this piece here is installed incorrectly. Okay. Again, it doesn't grip as much as you think it grips. It's a very fragile gripper. Okay, so it grips very lightly, and so every now and again you see the learners, and then the whole thing falls apart. What also happens is they don't program to time, so they program for rotations. And then this one here, this arm and this arm, if they're going to rotate, say, for 4 rotations, they're going to complete the 4 rotations. So the 2 arms actually collide with each other, and then they just break off, and it's just like one big mess. All right. I would say you need to have the arms measured that they're not too long, and also that your rotations are on time and preferably slower rather than faster. I know yeah. All right, so you've got the power. I would suggest that you build every single power attachment and you attach it to the robot, and then you've got to write a program to see whether it actually functions as you require it. Okay, but you must use rotations for a power attachment. There must be time. It must not be degrees or right. So if you're going to move, just to give an example, if you're going to move the arm, so there's your A, where am I here? So this is the A motor. I tested, you make a small test program and say, okay, so what's going to happen if I go up for 1 second? Okay, then you go up for 1 second and say, okay, so now it goes up. So then to let the arm come down, you're going to have negative 20 seconds. All right. And please use a weight before you change direction from up to down. Okay. And if up is positive, well, then down must be negative. It's as easy as that. Okay, so there you go. There you goes. And you can spot the error here. Okay, so we're going to go up here. We're going to wait a second. Then we are going to go forward for 2 rotations. And we're going to wait. And there's the error, because now we're going to go down for 1 rotation. And it could be that the arm is not high enough, and so it will actually never go down all the way. Okay. Again, with a gripper, you need to have a starting position. So either your gripper stays open or stands closed. And again, you would need to test which is positive to go open or closed. So I really suggest now that you take this list of all these attachments, all these power attachments, so you can build the gripper and the cargo loader are kind of the most important. There's a number of arms that you can build. You can build a forklift. You can build something with a rack and pinion. But all the combinations of power attachments, build them and then actually write some program. Okay, so you can just make sure that you understand. A good thing also is to make the robot move forward, move the items, and then come back. You can start with any items, but it's have a diverse collection of items that you can test it before you even start. All right, and then try with additional items to see how efficient it is. Can the arm maybe do from a tin of condensed milk to I don't know, tissue, and see whether it actually works. All right, there are a lot of very gear specific videos which you can watch. Dog gears are always my favorite, because you are actually working with kind of engineering as well. Okay. And then most of my ideas come from this winning design. It's for the EV3. It's from No Starch. I haven't seen the Spike Prime winning design yet, so I'm hoping it's going to come out soon so I can order something. But it really is, for me, it works. I'll show you an example now. But I would suggest for gearing, build at least one of those models. Maybe get in your class to build different of the gearing models, and then get your learners to compare. Because the other thing would then be everybody needs to build a power attachment, attach it to a robot, and try and do a mission, and then compare the effectiveness of each of the attachments. All right. Thank you very much. I'm going to stop sharing. Are there any questions? Any questions? Here we go. All right. So what I wanted to show you, let me just have a look here quickly. I think I do have one attachment that actually fits onto the robot. Or maybe I don't. Oh gosh. Okay. So what you're doing is you build. I would recommend you build just the chassis. All right, and then if you're doing the Riley row, this is a Spike Prime. So this has got attachments. So this fits onto here. This clicks onto here with pins. All right, and with that being pinned on, it's the gearing here is making connection with the dog gear. So that means it'll turn. So then you'll have some. Yeah, you can't. Oh, please remember, if you've got gearing, you can't turn it by hand. You've got to actually wait for the motor to turn. Time and time again, I see learners pushing these things. If it's anything with gearing, don't do it by hand. You've got to have a backup program that you can get it back to the original state. But this bevel gear is certainly, you can see if I just wiggle it a little bit, it is controlling the arm. Okay, where the power comes from is the motor inside here. All right. I did want to show you two things. Just give me half a minute. right. So I just want to show you some of the books that I have in my library, and you don't have to use all the books, but they're on that no starch. I found them on that no starch address. This is a really cool one. It's just EV3 ideas, and maybe you'll never need some of these structures, but sometimes this is fun just to build. And so these are just structures. Yeah, and of course it's the no wording, so there's no words. You just see what the pieces are. But then what I really encourage you to do is then to build the model. Just build it, and then see whether you can do a program to see what does it do, how can you use it maybe in your robot. Okay. And I think especially those teams that have finished celebration events and are maybe just looking for some additional activities, maybe these are really cool activities to do. It's just to build something just for the fun of it and see whether it's a okay, there's a thing with a cam, and it's really just structures that you can, models that you can build. All right. The other one, if anybody's going to take gearing seriously and engineering seriously, this is the so this is another really cool book to have, and it's the Unofficial Lego Technique Builder's Guide. This has got much more about gear. Oh, my cats have got hold of this book. Okay. There are many more structures, but it makes it good reading. And I think especially if you want to encourage your learners to kind of go into the engineering and to know what they're doing, maybe that's also a good handbook to have when you read and you've got nothing else to do. Okay. All right. Where do you start? I would definitely start, say, with a Riley rover or some building instructions that include some gearing and some attachments. First, build from building instructions. First use the building instructions. That's your very first stop. And once your learners understand how those attachments work, then you can maybe use some time to say, okay, so we understand how that works. Let's quickly see whether we can modify it a little bit. Okay. The dog gears is a good gearing kind of transition when you start exploring different structures. So use the dog gears and then start building different models, different gearing models, and seeing where it goes. Even just the gear train fascinates students always. And you can just start with a smaller structure, start with small gearing models, and then move on. But I do suggest that whenever you build a model, connect it to the brain and do some programming with it to see how it moves and what kind of power settings you need to make it move, and see whether it does anything. And then maybe for the fun of it, say, all right, so we have this little structure, what can we do with it? Okay. All right. Any questions?
If anybody has a question, please feel free to raise your hand or put it into the chat area.
Okay. If there's no this session is very practical, and I really encourage you to start building some structures, but maybe then also tomorrow when I do the last presentation, you'll see how do we apply it, how do we use these funny structures in solving missions. All right. Okay. Then we have a short lesson today. If there are no further questions, that was powered attachments, how to program it and how to build it. Stick to the basics, stick to the yes. Ms. van der Berg, yes. Okay, we can't hear you.
Can you hear me now?
Yes, there we go. Yes.
Okay, brilliant. Okay, so for the MOOC assignments, if you have to build a specific robot from building instructions, and for instance, the building instructions aren't perfect, like there's errors in it. Can you modify them for the assignments, or do you have to choose?
Which building instructions are not working?
I got it from the Droid board IV for the Spike Prime. There was some parts that didn't make sense using it.
Okay.
But I just want to know, is there like a grace on specific parts used?
Yeah. So normally when I use building instructions, the lesson I'm trying to teach is that you can follow instructions. And so like for the for the EV3 Riley Rover, we kind of stick to the Riley Rover building instructions. If you encourage your learners to start modifying as they go along, then you might not get the final result that you need. So I would, you can change the building instructions if you want to, but you must know what the consequences of that are. Okay.
Okay, that makes sense. Thank you.
But for a competition, you can come with a robot you've designed, you've manufactured, you've built. It's all good. Yes. Yes. All right. Thank you. Good question. And just on that is that for most of the attachments, these attachments, there are no building instructions. The learners kind of modified. I'm quite sad that I've never captured this in like Digital Designer, because there's some really good structures. You see this? So this is connected to a dog gear, this piece here. Yeah. So that's just, but it's amazing how the kids develop in attachments. Also, if you show them videos of saying this is what we can build, and let them build just the attachment, and then say, okay, so how do we use it? All right. Okay. Yes, Louise.
So if we do the assignments and we use the instructions and we put that in our portfolio, you won't see it as not something that we originally thought of ourselves. We're allowed to build something that's already.
You can just say in the instructions, or just say when your submission, you say you initially used the URL, the following URL, and for inspiration, and then you modified it. Okay. I think it's
so
also
just add stuff of our own, like to make it more original.
Absolutely. I've also noticed in competitions where learners are like very assertive in the fact that they built the robot. You might have built it, but it's not your design. So you also need to teach your learners to give due where due is due, because that was not initially their design. All right. And it's nothing wrong with saying we started building the Riley Rover and then modified it like this and we added that. That's fine. The judges are actually looking for a progression of innovation. So you start somewhere, but where did it take you? What did you do with the stuff that you got? Yeah. All right.
Okay, thank you. Great.
Awesome. So just on that, we have a holiday program at the beginning of October for 3 days, and so the schedule will go out hopefully this afternoon, maybe tomorrow. But just join us for a day and come and do some practical stuff with us. It'll be great to see you, and it'll be great to meet everybody as well. All right. We just have very limited space, but if you, once the invitations go out, it'll be great if you can join us. All right. You have to reserve your place. Okay. Excellent. All right. Thank you very much, everybody. Thank you, Casper, for recording. Thank you to Cabello for opening the ceremony, the session. Tumelo, do you want to close?
Dr. Gous, I saw Ms. V wanted to say something maybe.
Oh, okay. Hi, V.
Hi, I just wanted to say thank you so much. It's like when it comes to gears, yes, it's a grade 8 content. So what we don't know is how to use them in attachments and program them. So I think the practicals will be shedding more light to us.
Excellent. Excellent. So you're going to join us. Good idea. Otherwise, we'll do some more demonstration hands-on stuff. I think we'll do that. All right. Thanks, V, for that. Awesome. Right. Tumelo, would you like to close the session?
I wouldn't like to close the session, but because we don't have any other questions, I'm forced to. To our online participants, thank you so much for being part of today's session. And for those that are watching the recording, thank you for taking the time to watch the recording. Dr. Gous, a very big thank you. Thank you so much to the team as well. It's a happy Wednesday. Goodbye.
It's a wonderful Wednesday. Absolutely. All right. Thank you, everybody. And let's see each other tomorrow then. Thank you. Bye-bye.
All right, bye.
Bye-bye.